Okay, so this is lecture 10, and we will continue with our discussion on charge pump based PLL. Do you have any questions? Okay, so at the very end yesterday, we just drew the block diagram of a charge pump based PLL. So let me make it again for today's thing. So we have ICP current, this is switches up, and all these can be your CMOS switches. Current is ICP, both top and bottom current, which is pushed into loop filter. And yesterday we saw why we use this kind of loop filter, RC1, plus another capacitor which is used for ripple suppression for now. And then we had a VCO. Okay, so this was the block diagram we had yesterday. The output of the PFT is phase error, which is measured by the PFD. Okay, and this part is charge pump. This one is loop filter. Okay, okay. So okay, this is connected, not. Oh man. Okay, fine. So let me just. Yeah. The input of this is phi in, and the output is phi out. Okay. Now the small signal model of above PLL is PFT gain is 1 over 2 pi. Charge pump is ICP times, then you have this loop filter. I am still drawing it. We can calculate the impedance of this loop filter. What's happening today? Okay. You this fine. R C1 C2, and then you have KVCO over S. Phi in, phi out. This node is phi error. This one is V control. Okay. So now the loop gain of this PLL is 1 over 2 pi into ICP, and if you find the total impedance for this loop filter, it will be 1 over SC2 into S plus 1 by RC1 into S plus 1 by RC1 C2 by C1 plus C2 times KVCO over S. Okay, which can be just clubbed together. ICP KVCO by 2 pi into S square C2 S plus omega Z and S plus omega P3. So here your omega Z is 1 over RC1 and omega P1, omega P2 is 0 and omega P3 is R into C1 C2 by C1 plus C2. So now the thing is, how do we place all these poles and zero to get an desired gain and bandwidth for the PL? Okay, and this is an open loop gain. So let me just plot the loop gain in terms of omega z and omega p. So say this is your omega axis. So two poles are at 0, so I have minus 40 dB per decade. Then I have a 0, and it can be something kind of this. Omega z, this one is omega p3, and this is omega u. Okay, this is mod of loop gain. And I also want to plot the phase of the loop gain. So what is the phase of the loop gain? Angle of loop gain is equals to minus 180 plus tan inverse of omega by omega z minus tan inverse of omega by omega p3, right? So it starts with minus 180 degree. Let's say something here, minus 180 degree. At omega z, it will be minus 135 degree, right? And so it will be something close to like 90 or whatever maximum, and then it again comes back to here. So this one will be, you have omega p3, it goes, so let me just plot it slightly. So I have okay. You can plot it to scale, but I'm just plotting it like this. Okay. So what is the phase margin of, so this is your omega unity gain frequency, and the phase margin of this loop for this PLL will be this, right? Where the loop gain equals unity gain frequency, loop gain equals to 1 and phase equals to 180 degree. So now the question is, you can see I can vary this unity gain frequency, means I can vary the pole placement omega p3 and omega z, okay, to have the same unity gain frequency. So whether this is good, or let's say this will not be that clear. So just for an example, let me put it like this. So let's say the phase margin roughly at actually here the unity gain frequency will change slightly, but let me say here in the red one and the blue curve, let's say the unity gain frequency is somewhat farther or farther or some, this is like this. Let's say it is somewhere not at the peak. So do you see any problem, or not any problem, means what better can be done? So let me just say, if your phase margin, let's say in the previous red curve, right, your unity gain frequency and your phase was not at the peak of the phase value, means if suppose the unity gain frequency was here, then your phase margin was this, right? But you are not on the peak, you are somewhat away. So anything which you can think of is can be done better. Better in the sense, so let's say if you are not on this phase angle phase plot, you are not on the peak, you are somewhat away. Then when you design a real PL, pardon? No, the thing is omega P3 you can push further right side, but then you will see the ripple suppression thing. So you want a certain ripple suppression also. Okay. Now the only thing, this is more with respect to the real implementation. So if on the phase curve your unity gain frequency is placed such a way that your phase margin is on the downhill slope, or let's say uphill slope, if the unity gain frequency lying somewhere there, then with a slight variation in the component parameters, you will see a change in the phase margin. Whereas if you are at the peak, if your component parameters change slightly, in the same variation, if you look, if the slope is 0 at that point, then the phase margin deviation will be lesser with the change in the component parameters or any loop gain parameters. Right. So this one is, so let me just say, in case, so any of this red or blue curve, they correspond to your suboptimal phase margin design. Suboptimal phase margin. Whereas if you have, I do not want to plot on the same, so let me just, if I have something which is just, okay, now how this omega P3 and omega, all those things will play out, we will see that. If I am here, right, then the variation in the phase margin will be lesser. So this one would be correspond to your optimal phase margin, right? So I need to place, so the thing is I do not want to change my unity gain frequency, still I want the same unity gain frequency, but I want to place my 0 and poles in such a way that I get the phase characteristics from here. And in addition, whether your ripple suppression will come out to be the same or not, you need to check that. Okay. So let me just say what should be the condition for the, if I want to get this, so parameters we know. So okay, let's see. Desired parameters are omega u and the phase margin, because phase margin will finally decide your stability of the system, right? The component, the parameters which you need to find means in terms of R, C1 and C2 is your omega Z, omega P3 and your ICP. Okay. The other parameters like KVCO, this is the this is the characteristics of the voltage control oscillator or current control oscillator, and you will have a certain range, or you can have a certain gain on the oscillator, right? So you can change the gain of the oscillator, but then you will be, so let me just say this, if you want to vary delta F by 1 gigahertz, let me just say, right, and you are working with the supply voltage limit of 1 volt, whichever means, if the supply limit is 1 volt for the oscillator, then you cannot change the voltage by more than 1 volt, typically speaking. So you need to, means this, I am talking of a very extreme case, that I can have a delta V control maximum of 1 volt, right? So then my, means ideally what I want from my VCO, if I change by 1, this is all depends on the control of the oscillator. Okay, so I should have a 1 gigahertz of change. Okay, now if I want, just for, if this 1 volt reduces to 100 millivolts because of some circuit parameters, and I still want my 1 volt thing, then your KVCO will go high. So KVCO is not only means it's not only controlled by the oscillator independently, but it is also controlled by the range which you want to exercise with the loop filter. You can still manipulate it, but right now let's say you get the certain KVCO. Okay, so omega Z and omega P3 and ICP are the 3 parameters which you need to find, and so the condition for an optimal phase margin So let me just optimal phase margin. If I want the derivative to be equals to 0, what shall I do? And this is a simple d phi m by d omega evaluated at omega equals to omega u should be equals to 0. So now see what this condition leads to. So your phi m is equals to tan inverse of omega u, or omega, right now I'm writing with respect to omega u because we are evaluating at omega u, by omega z minus omega u by omega p. So did I anywhere define phi m? Means I just showed what is phi m. So this is equals to angle of loop gain minus 180 degree at unity gain frequency. So let me just rewrite that. Angle of loop gain evaluated at omega equals to omega u minus of minus 180. I just wrote it because let's say if next I will introduce another pole, this is the formula you use. Okay. So now derivative of phi m with respect to omega u is 1 by omega z by, I can give you the direct equation, but I do not want to scare you with the final equations. That's why I'm driving here. So sorry, this one was okay. So omega u by omega p3 whole square, right? And this derivative should be equals to 0, which implies I have what, 1 plus omega u by omega c whole square is equals to this derivative. Okay, this is times omega z by omega p3 and 1 plus omega u by omega p3 whole square. Okay, now I just want to take omega u whole square on one side, so that will be omega z by omega p3 minus 1 is equals to omega u square omega z by omega p3 times 1 by omega z square minus 1 by omega p3 square. Just let me know if there is something wrong here. This derivative goes to 0. I just put equate it to the left and right terms equate. Translate that there. This one goes omega z by omega p3. This one right. So what you have, p3 minus 1 and omega u square by omega z square and omega z by omega p3. Okay. So this thing cancels out. So what I have, omega z by omega p3 minus 1 is omega u square by omega p3 into 1 by omega z minus 1 by omega p3. Okay, so let me just write this as, is there any sign? Okay, yeah, there is one sign issue here, right? This should be plus, this is minus. Okay, so I can very well write this equation as omega u square by omega p3 square into, sorry, I don't want omega, so I will take omega p3 and omega z as omega z by omega p3 minus 1. Okay, so means you take the other term, omega z can't be equals to omega p3. So omega u is equals to under root of omega z times omega p3. Okay. Now looking back, where I wrote omega z and omega p3, you can say omega p3 is equals to omega z by c1 by c2 plus 1. Right? I just took 1 by rc1 as omega z, c1 plus c2 by c2, that is thing. So this will be equals to omega z times 1 plus c1 by c2. So this is the condition which you get for making the derivative of the phase equals to 0. But at omega u, but till now I have not put the phase margin which I want. So now phase margin is equals to tan inverse of omega u by omega z, which is 1 plus c1 1 plus c1 by c2, and the other part is, we have just seen that omega p3 is equals to omega z times under root of into under root of 1 plus c1 by c2. So this one is omega u by omega p3. Omega p3 is omega z times omega z times not under root but 1 plus c1 by c2. Okay, so this term will translate to happening today. So this translates to tan inverse of 1 by under root of 1 plus c1 by c2. So now phase margin itself is equals to tan inverse of 1 plus c1 by c2 minus tan inverse of under root 1 plus c1 by c2. Okay. So I take tangent on both the side. Since I know phi m, so I know tan phi m, which will be, so now I am applying tan on tan inverse a minus b, so which will be equals to your c1 by c2. So let me just write it as under root of 1 plus c1 by c2 minus 1 by under root of 1 plus c1 by c2 into 1 plus 1, right? So this is, I think this is the formula, if I remember it right. Tan of a minus b is tan a minus tan b divided by 1 plus tan a tan b. Pardon? Because they are just the reciprocal, so that cancels, right? So this one will be c1 by c2 divided by 2 into 1 plus c1 by c2. Okay, now you can take the square and do all the maths. So what you have is c1 by c2 whole square, okay, minus 4 into 1 plus c1 by c2, tan square of phi m goes to 0. Okay, so c1 by c2 ratio will be 4 times tan square of phi m, that is minus quadratic equation. So this will be 16 times 10 power 4 phi m plus 16 times tan square phi m by 2, which will be your 2 times 10 square phi m plus 2 times, I will take 10 square phi m outside, so this is 10 phi m out into tan square of phi m plus 1. So just writing it in more abbreviated form, this is tan of phi m by Discuss them. Okay. So this result is, we got this result after putting the condition, means after. So let me just say what all things are present in this equation. This equation has whatever omega u you wanted, for that omega u, whatever phase margin you wanted, and derivative of phase with respect to omega u is equals to 0 at omega u, right? So you got the component relation in this manner. Okay. Now, so let me just list it as a design procedure, because this is all we need from equation as such. Design procedure for type 2 order 3 charge pump based PLL. Okay. First one is, this is what you have, omega u and phi phase margin requirement. Okay. Now this omega u will later be changed, but let's say you know right now omega u, what do you want? From this omega u and phi m, you got, let me just define the term as Kc equals to C1 by C2. You got this value, 210 phi m into. So I write this equation, but please verify if something is wrong, let me know. And don't basically just use it as it is and then say, sir, this was wrong, so my PLL output was wrong. Okay, but the procedure is this only. Seems like I'm going a little bit fast on this. Okay, so once I know Kc, what parameter can you find? You know omega u, you know C1 by C2. Just look at what are the parameters we have. We need to find. We need to find omega z and omega p3 and ICP. So omega z is just a function of omega u. So where was omega z? Omega z is omega u by under root 1 plus C1 by C2. Right? So from using that, I have omega z is equals to omega u by under root of 1 plus Kc. I got this. Okay. Then you have to make a choice now about, now this is component parameters. So from here you can find omega z and omega p3. That is not a, I mean that's a easy thing, right? Omega p3 is just nothing but omega z into 1 plus Kc. Now you come into the component values R, C1 and C2. So you have to make a choice for R. Now this is choice. No, phi m is not given to be. Phi m is some parameter which you will define for the stability thing. Okay, so there will be a trade-off if you choose a larger phi m, and if you choose a lower phi m, surely stability is a thing. If you choose a larger phi m, there will be a trade-off. So that trade-off you will, so there will be trade-off in terms of noise, trade-off in terms of capacitor area. So you will see that thing. So those trade-off you can see. So I can, let's say I start with something, I say I will go with a very stable system, 88-degree phase margin. But for 88-degree phase margin, you may end up having a capture of 1 nanofarad. So can you have that 1 nanofarad capture will be a question. So then you say, okay, I will go for 70-degree phase margin. 70-degree phase margin, you will have a capture of 100 picofarad. Question is, can you still give that area for 100 picofarad of cap? Right? So those trade-offs will come, but that will come in the design process. So if you follow this design process, all the variation of the parameters is before you. Then you have to just make the choice there. Now the choice for resistance. So resistance area is normally not that a problem, but choice for resistor is mostly based on noise. So till now we have not I can say we have not considered any noise in the system, right? So Your charge pump is noisier, your PFD is also noisier, divide, everything is noisier. So all this analysis will be done in the presence of noise. So what should be the final goal? The final goal should be I want a minimum noise output. So the parameter which I have chosen here like omega u and phi m, those parameters are coming after doing the noise optimization, the final value. So it's like this. You start with a certain omega u and phase margin. You see what is the noise, final resultant noise. Then you vary omega u. So let me just show you once I complete this how this omega u and phi m come. We will deal the noise later. So choice for R is based on noise. Once you know R, your omega z is equals to 1 by RC1. So this will give you R. Sorry, C1, not R. Right? And you already know Kc. So this will give you C2. So you means you choose R, your C1 and C2, you got it. Okay. Then the final one is what is ICP. So for ICP, we know that the mod of the loop gain is equals to 1 at omega u. So let me just say this loop gain at omega u is equals to 1. Right? And so what is this? This is equals to, if I have, this is going full screen all the time. So, okay. So this one is ICP KVCO over 2 pi, right? Omega u square C2 times 1 plus, not 1, but this is square, omega u square plus omega z square by omega. If anything is missing, you can add it to it. Omega p3 square is equals to 1. We started with KCP, so this will give you ICP. Okay. So for a given choice of omega u and phase margin, and the other parameter which you choose on the way was R, you get all this R, C1, C2 and ICP. Okay. So now for this loop gain, if I plot mod of loop gain, I will have, let me just start little bit. Okay. Okay. Then the phase margin of this, this one is omega u, omega z, omega p3 and omega. So phase, so let me just get this here. This line is not straight. Anyways. Okay. And let's just mark it that way. So it is start with minus 180 degree, and it will have, means I think if you follow all these equations, it will be like this. So this one is omega u, and the phase margin is, let me just start. This is phase margin. Okay. So this one is angle of 50. Means there is no way you can mess this analysis and get and you do not get these characteristics, let me say. And for a low frequency PLL where technology is also not causing troubles, you can get this thing even in a real time implementation. Okay. So now the thing is the choice for omega u is, are there any questions till now? I have completed too much maths today, so anything. Yeah. Why both the things? It's a geometric mean of that, right? It's not a arithmetic mean. You say the difference should be the same. No, I why? So let me just give you a. Let's just pick up a number, right? So it's 2, 4. So let's say what is the geometric mean of 4 and 60? 64, right? 64 is the square, and geometric mean of 64 is 8. But 8 is not equidistant from 4 and 60. 4 and 60. So has been an arithmetic mean, then it would have been a different case. Okay. So it is surely what you are saying is right, that omega z is constrained by the placement of omega u and omega p3. That is right. But it is should not be the equidistant, should not be equidistant from omega z and omega p3. Okay. So right now I just means whatever we have got there, the placement of omega p3 got fixed because of the phase margin. I do not have that much freedom right now to place omega p3 where I want to suppress the ripple. Yeah. Yeah, that's what I was just saying the same thing. I have not done anything on the ripple suppression part, right? But I know the second pole placement is doing something for the ripple, right? So now if I change my phase margin, okay, my phase, when I change the phase margin, then my omega p3 placement is going to change. Then my ripple is going to change. So the thing, so you can say for the ripple suppression, there is a placement of the second pole. Okay, but how much ripple can I suppress? That is actually dependent on the phase margin, because these things are governed. So you can calculate it back. If I have this much of phase margin, I have this much of this much of phase margin. If I have this much of phase margin, how much ripple suppression can I get? Okay. Any questions? So in all this case means right now I will just show you how do you get omega u and omega. Okay, let's say what are the effects of smaller and larger phase margin other than the stability? Means okay, stability is surely there with the phase margin. What can you observe in the closed loop gain of the PL? This is again an open loop gain only, right? This is not the closed loop gain. So let me just plot a closed loop gain for this. So phi out by phi in, this is now a closed loop gain, will be loop gain by 1 plus loop gain, right? There's nothing wrong here. So let me just plot. So let me just call this as a closed loop. So closed loop gain CL of S. Okay, so this is a 0 dB line, right? So let me just extend the picture, zoom in the picture a little bit. So let's say this is your minus 3 dB bandwidth. Just for example, this is minus 3 dB bandwidth. Okay, and this particular curve, let me just say this is for the phase margin of, okay, it should be, let's say 70 degree. Actually 70 degree will have some slight peaking, right? Now if I change the phase margin of the loop gain, let's say I have a phase margin of something as 45 degree, okay, and I want the same unit, same minus 3 dB bandwidth. Okay, so what do you think will change in the response? The DC response remains same. Okay, what will change slightly is the peaking in the response. So, mhm. So I will have a peaking. Wow, this is interesting. And this will also be the same flow, but means you can have the similar slope. But the concern which I am trying to say here is this one. Okay. So phase margin will directly be reflected in the peaking which you see here. Let me just peaking in closed loop response. What will this lead to? This will lead to a ringing in the phase output. When you give any step, any input changes, there will be a ringing in the output. So that is the first artifact of a lower phase margin you will see, other than the stability. Means if the 45 degree, it means if you have, ideally if you have a phase margin of 45 degree or 60 degree, right, if there is nothing else in the system which is going to change this phase margin, you are still stable. Okay, so stability is not compromised, but the only thing is how much headroom do you have in one place, and the other thing is how much peaking are you going to have in the on the frequency response. So peaking in the frequency response leads to a ringing in the time domain response. I think that part everyone understands, right? And the other thing is that right now I have not shown any noise characteristics. Now, if there is a peaking in the frequency response, you can say all the noise sources which are coming from closer to the input, that seems like a PFD or the reference noise or the charge pump noise for that matter, they will be amplified. Okay, so peaking will at some point will also lead to an increased noise in the system. No, so the thing is, let's say the reference noise is a white noise, which is all right. The charge pump noise is again a white noise. So all the noise sources which are white noise sources and are closer to the input, we will see that in detail. They will get amplified with the peaking. Now, whether they amplified more or less, that's again a study. Okay. So that is with regard to the phase margin. The other thing which I was saying, how do you get your uh, omega u and your phase margin? So phase margin you can see with the ringing or the peaking, and the other part is the noise. So I will just give you the uh, what are the main noise sources in the system. So yeah, any question? No. So the thing is, so it will be when I say the ringing in the step response, right? It settles down over after a long time. It will ring. Now, how exactly does it translate to jitter? That would be a little hard to say here. I do not know. Means this thing is. So let me say all these noise analysis are a small signal analysis itself. So when you give any step to the system, if the step is very small, right? If it is not a large step, if the step is very small and all these loop gain analysis hold valid, then it will add to the jitter. But how exactly does it comes as a jitter? That is, I think that depends. Okay. So when we look at a ringing in the step response, the step actually the step at the input excites all the frequencies. Okay, so all these frequencies will then translate to the jitter. Okay, so yeah, so I was saying that this omega u and omega, sorry, how do you get omega u? So there are two main noise sources right now I'm talking. One is a charge pump noise. The charge pump noise is at the input, right? It is at the PFD, it is input, you can refer it to the input. The noise transfer function for charge pump noises, sorry, this is pretty bad, low pass, is like this. Okay, so I'm just saying this is the noise transfer function, which is NTF of charge pump. So NTF is NTF of CP is noise transfer function for charge pump. That is like how the noise from the charge pump is being translated to the output. Okay, and actually the noise from the VCO has a high pass transfer function. This one is NTF of oscillator. So the problem in the very conventional design is that if you reduce the bandwidth, your VCO noise will dominate. If you increase the bandwidth, your charge pump noise will dominate. So you need to have an optimum bandwidth such that the total noise is lesser, right? So what we do is we actually vary the unity gain frequency. We will deal with in detail. I'm just right now showing you that how do I get the unity gain frequency. So we choose different unity gain frequency, let me say omega u, and do this analysis in the presence of noise and find what is the total noise. So you will find that this will be something kind of this characteristic. This is, let's say, total noise. All the units and all you look in detail. So the region where your when omega u is lesser than some value, in this region actually your charge pump noise dominates. Considering there is only charge pump noise, not the reference and others, and in this region your VCO noise dominates. Okay. So you do all the analysis which we have talked in the presence of noise, and you find what is an optimal bandwidth for the given noise sources. So either you choose that bandwidth or you go and change the noise sources themselves. Spend more power. So you get your omega u, and for each omega u, you have the same analysis. Okay. Any questions? So this part completes such like a very basic design of a charge pump based PLL. And the only thing I think you all would have noticed is that I have not used this as a clock multiplier. I have a gain of 1. So what changes if I want to use a charge pump PLL as clock multiplier? Okay. The only, so let me just plot that or draw the diagram for that. I have PFT, charge pump, loop filter, then VCO, and what changes here is your division factor, frequency divider. And this is the frequency divider, so the phase gets divided by the loop gain for, yeah. It divides the frequency and the phase gets divided. So it's a clock frequency divider. You do not, so one thing is, so it's like this. The input is this, so let me just ask you this. So you have seen a clock divide by 2, right? I have a clock and Q and Q bar. This is out. Okay. So let me just find. Okay, this is out. In. Right? So you see that if the input was this, right? The output divided by 2 will be, this is a frequency divider, right? Now whatever phase error or any, means we are talking of all this in terms of error because everything is in a lock condition, whatever is at the input, yet that particular thing gets divided by the, means when it is now referred to the divided clock frequency, that will be now become a divide factor. You get that logic. The thing is, let me say this. Let's say there is a delta T error at the input of the divider, right? The delta T error will not change at the output. It's absolute time. So if I shift the clock, if I shift the input clock by delta T, right? The output clock will also get shifted by delta T. It is not, so the thing is, the divider itself is not adding anything to it. Okay. But now when that delta T gets shifted, is introduced at the output, now the output frequency is half the time. Right? Now you refer to the output frequency because now the phase is always with respect to a frequency. So in this case, so yeah, this is very, so the output of this, let's say, is phi feedback, right? Now phi out is with respect to the output frequency. Phi feedback is with respect to the reference frequency. Now you get the logic, right? If you are doing an absolute time analysis, it will do that. Okay. So yeah. So the thing is, this particular, as soon as we introduce a divider in the feedback loop, this acts as a clock multiplier where your F out is really interesting. F out is equals to n times F ref, and your loop gain remains, means most of the part remains the same. The only thing changes is 1 plus, sorry, S plus omega z by S plus omega p3. Let me have KVCO here. And the only factor is 1 over n. So now you have to accommodate this n factor mostly in the mode of loop gain only, nowhere else. Because everything else is in terms of phase, or because we did most of the analysis on the phase margin with respect to unity gain frequency. So you can do the whole analysis and it will be a clock multiplier. Okay, so let's stop here. Any questions so far?